Imagine waking up in a universe where you shouldn't exist. Every particle of matter would have its antimatter twin, and upon meeting, both would disappear. And yet, here you are. This audiobook explores one of the deepest enigmas of physics. Why is there more matter than antimatter? Why did the universe break its perfect balance? The answer may lie in the first moments of the cosmos, and explain why everything you know exists. Symmetry, in simple terms, is that quality possessed by objects or the laws of nature that remain unchanged under certain transformations. For example, think of a mirror. When you look at yourself in it, the reflected image is a symmetrical version of yourself. But what happens when we take this concept to the realm of the universe? The reality is that although symmetry is fundamental to many scientific theories, there are surprising exceptions that lead us to question what we think we know. Let us ask, why is symmetry so important in physics? The answer lies in the fact that many of the fundamental laws of nature are based on symmetrical principles. For example, the conservation of energy and the conservation of momentum are concepts that arise from symmetry in time and space. However, when we examine the universe as a whole, we encounter a series of puzzling asymmetries that challenge our understanding. One of the most intriguing questions is, how does the lack of symmetry influence the creation and evolution of the universe? Imagine the universe as a vast canvas on which the rules of physics are drawn. Instead of a perfectly symmetrical design, this canvas presents stains and wrinkles that tell us a different story. Each of these imperfections may be crucial to understanding how we came to be and how the reality around us works. Asymmetry also plays a vital role in how we perceive the world. From the structures of crystals to the arrangement of petals in a flower, nature often chooses a path that is not symmetrical. This phenomenon raises fascinating questions. Why do these differences occur? What do they mean for us and for the universe as a whole? As we explore these questions, we begin to unravel a cosmic fabric that is both beautiful and complex in the realm of particle physics. Asymmetry becomes an even more intriguing topic. Did you know there is a subtle yet significant difference between matter and antimatter? This imbalance is one of the keys to understanding why the universe exists as we know it. If matter and antimatter had been created in equal proportions, the universe we inhabit would not exist. Thus, asymmetry is not just an abstract concept, it is the reason behind our existence. Let's take a moment to think about the expansion of the universe. As it expands, new asymmetries are also generated. Galaxies cluster and separate, creating a structure that is anything but symmetrical. What implications does this have for how we understand the cosmos? The answer to this question is fundamental to modern cosmology and helps us glimpse the history of the universe from its earliest moments. Gravity, that force that keeps us grounded, also introduces its own form of asymmetry in space-time. This interaction not only affects large objects such as planets and stars, but also has a profound impact on how the universe is structured. The irregularities in how gravity acts on different celestial bodies create patterns that are anything but symmetrical. When we talk about cosmology, it is essential to consider how different models have attempted to incorporate symmetry and asymmetry in the evolution of the universe. Throughout history, scientists have proposed various theories that try to reconcile these two seemingly opposing forces. However, as research progresses, it becomes evident that asymmetry may be an intrinsic feature of reality. The theory of cosmic inflation, for example, suggests that the universe experienced an extremely rapid expansion in its early moments. This phenomenon not only helped shape the structure of the universe, but could also offer explanations for certain asymmetries. The idea that the universe began to expand unevenly raises profound questions about its origin and nature. Delving into the mystery of dark matter and dark energy, we find more examples of how asymmetry in the universe can influence its structure. These components are fundamental to understanding how the cosmos works, yet their nature remains an enigma. As we delve into their complexities, a crucial question arises: how do they affect the symmetry of the universe as a whole? Finally, reflecting on asymmetry in the universe leads us to an unexpected place: life itself. How has the lack of symmetry allowed living beings to emerge in a constantly changing cosmos? The answer to this question is as rich and varied as life itself, inviting us to explore the connections between science, philosophy, and existence. At the end of this journey, what becomes clear is that asymmetry is not a mere accident, but a fundamental piece of the cosmic puzzle. It drives us to continue exploring, to question, and to marvel at the vastness of the universe. The quest to understand why the universe is not symmetrical is not just an intellectual exercise, but an invitation to discover our own story within the fabric of reality. So, are you ready to continue unraveling these mysteries of the cosmos? Symmetry is a fascinating concept that lies at the heart of many scientific disciplines. To understand it, let's think of an everyday object, a circle. When you look at it, you may notice that it looks the same from any angle. That uniformity is what we call symmetry. In simple terms, symmetry refers to a balance, a harmony that repeats. But why is this concept so important in physics and cosmology? Symmetry is not just an aesthetic issue. In nature, symmetry manifests in repetitive patterns and the organization of structures. From the wings of a butterfly to the molecules of a crystal, symmetry speaks to us of an underlying order. But what would happen if this order did not exist? How would our understanding of the universe change? The answer is intriguing, and it leads us to explore how symmetry applies in science. In the world of physics, symmetry has an even deeper meaning. It relates to the laws that govern the behavior of particles and the forces acting in our universe. Many of these laws are based on symmetrical principles. For example, if we throw a ball upward, we expect it to return to the ground. This predictable behavior is based on the symmetry of the forces at play. But what happens when this symmetry is broken? To understand it better, let's consider the concept of symmetry in time. If time were perfectly symmetrical, we could move backward and forward in it without noticing any difference. However, our daily experience tells us that time has a direction. The past and the future are different. This is a form of asymmetry that influences how we live and understand events in our lives. Asymmetry is not limited to time. It is also present in the way particles interact. In particle physics, there are cases where interactions are not symmetrical. For example, in certain reactions, particles and their antiparticles do not behave in the same way. This violation of symmetry may seem confusing, but it is fundamental to understanding how our universe works at a fundamental level. Often, symmetry is related to the idea of conservation. In physics, there are conservation principles that tell us certain quantities remain constant. For example, the conservation of energy tells us that energy cannot be created or destroyed, only transformed. However, when a violation of symmetry occurs, these conservations can be altered. This can lead to surprising answers about how matter behaves in the universe. Nature is also full of examples of symmetry that seem magical at first glance. Consider flowers. Many of them have a symmetrical arrangement in their petals, which is not only beautiful but also attracts pollinators. This type of symmetry in nature has an evolutionary purpose. But what about those creatures that do not follow this pattern? How does this affect their survival? As we explore these concepts, it is important to remember that symmetry is not an absolute fact. In the subatomic world, things are much more complicated. Symmetry can be a guide, but not a strict rule. This leads us to question the very nature of reality. If asymmetry can exist in a world that seems ordered, what does this mean for our understanding of the universe as a whole? The relationship between symmetry and asymmetry is also reflected in art and architecture. The most iconic works are often built on principles of symmetry, as these structures are pleasing to the eye. However, asymmetry also has its place in creation. Sometimes it is the lack of symmetry that creates visual and emotional interest. Isn't it fascinating how these concepts intertwine in various facets of our lives? As we delve deeper into the world of science, we discover that symmetry and asymmetry are more than just abstract concepts. They are tools that help us unravel the mysteries of the universe. They allow us to make predictions about the behavior of particles and help us understand the structure of the cosmos. But at the same time, they invite us to question our assumptions and explore the unknown. As we continue our quest for knowledge, it is essential to keep an open mind. Science is constantly evolving, and what we consider asymmetrical today may find a new balance tomorrow. The history of science is a story of surprising discoveries and unexpected turns. Who knows what new revelations await us in the future? Ultimately, symmetry and asymmetry are reflections of the complexity of the universe. They show us that, although we seek patterns and order, reality can be chaotic and surprising. This duality is what makes science exciting and challenging. By exploring these concepts, we are not only learning about the universe, but also about ourselves and our place in it. So, on this journey through symmetry and asymmetry, let us remember that each discovery brings us one step closer to understanding the vast and mysterious nature of the cosmos. Science invites us to question, explore, and above all marvel at the complexity of existence. Nature surrounds us with astonishing beauty and order. From the symmetrical branches of a tree to the shape of a snowflake, symmetry seems to be a fundamental characteristic of the world we live in. But what does this symmetry really mean? Why is it so important in nature and science? Symmetry can be understood as a balance or correspondence between different parts of an object or system. Think of a butterfly. Its wings are almost identical in shape and size, reflecting a bilateral symmetry that is not only beautiful but also functional. This symmetry is not just visual. It also manifests in the laws of physics that govern the behavior of particles and forces in the universe. But is this symmetry a universal principle? In nature, we find examples of symmetry everywhere, from the crystalline structures that form minerals to the proportions in the faces of living beings. Symmetry seems to be a guide for design. Have you noticed how many flowers have a specific number of petals? This repetition also reflects a symmetrical pattern that recurs in different species. But what role does all this play in our understanding of the universe? Every time a scientist observes a natural phenomenon, they look for patterns. Symmetry provides a foundation upon which theories and models can be built. However, not everything in nature is symmetrical. Why do asymmetrical structures also exist? The answer may be related to evolution. Asymmetrical shapes can offer adaptive advantages, as in the case of animals that camouflage themselves in their environment. Asymmetry, then, is not a defect but a survival strategy. In the world of physics, symmetry and asymmetry play a crucial role. For example, in the study of subatomic particles, scientists have found that some interactions are symmetrical, while others are not. This leads us to an intriguing question. If symmetry is a fundamental principle of nature, why are there exceptions? A fascinating case is that of crystals. These ordered solids exhibit symmetries that can be described mathematically. However, when we analyze more complex structures, such as the proteins in our bodies, asymmetry becomes essential. Proteins are like pieces of a puzzle that must fit together in specific shapes to function properly. Could it be that asymmetry is also a driver of diversity in life? Symmetry is not only found in the physical world, but also in the way we perceive art and beauty. Artists often use symmetry to create visually pleasing compositions. However, asymmetry can be equally powerful, evoking emotions and challenging our expectations. Why do some asymmetrical works of art attract us so much? Perhaps because they invite us to explore beyond the obvious, to find meaning in the unexpected. Symmetry and asymmetry are also concepts that help us understand the universe on a large scale. From spiral galaxies to the distribution of dark matter, the patterns we observe offer clues about how the cosmos was formed and evolved. But what happens when we consider the expansion of the universe? Asymmetry may play a role in how galaxies are distributed and how they interact with each other. Looking to the future, symmetry and asymmetry will continue to be topics of great interest in scientific research. Physicists seek to understand how these properties can affect theories about gravity, dark energy, and dark matter. What new revelations await us on this fascinating journey of discovery? Symmetry is more than an aesthetic concept. It is a key to understanding the laws that govern the universe. Asymmetry, though often overlooked, is equally fundamental. Together they form a dynamic balance that allows for the existence of diversity in the cosmos. How might these ideas change our perception of the world and ourselves? As we delve deeper into the study of nature, we encounter questions that challenge our conceptions. The search for symmetry and the understanding of asymmetry lead us to reflect on our place in the universe. Each discovery brings us one step closer to unraveling the mysteries that surround us. Contemplating symmetry and asymmetry, one might wonder, what does this mean for our existence? The answer may lie in the interconnectedness of all elements of the universe, from the smallest particles to the largest galaxies. Ultimately, symmetry and asymmetry are part of a larger whole that invites us to explore, learn, and grow. Nature, in its complexity, offers us a canvas where symmetry and asymmetry coexist in a delicate balance. In this journey of discovery, each question opens the door to new possibilities and understandings. So, as we look around, what other wonders can we find in this infinite dance of symmetry and asymmetry? Physics has revealed over the years that the universe is not a symmetrical place, but what does that really mean? To understand it, it is essential to delve into the concept of asymmetry, especially in the context of the laws that govern nature. Imagine entering a funhouse mirror room at an amusement park. Each mirror reflects your image in a different way, creating multiple versions of you. However, if one mirror is broken or distorted, that image will no longer be perfect. This is one way to think about how asymmetry can influence our perceptions and the laws that govern the universe. One of the most intriguing phenomena in physics is the violation of CP symmetry, which combines charge symmetry, C, and parity symmetry, P. This violation refers to how certain particles, such as kaons, behave differently when you swap their charges and positions. Isn't it amazing to think that, at such a fundamental level, the rules of the game can change? This idea that particles do not behave the same in all situations leads us to a new understanding of how the universe works. To put it in perspective, let's imagine tossing a coin into the air. If the coin always landed the same way, it would be an example of symmetry. However, if we discover that when tossed under certain conditions it lands more frequently on one side than the other, we would be facing a phenomenon of asymmetry. In the world of subatomic particles, something similar occurs. The violation of CP symmetry suggests that there is something deeper in the structure of matter that we have not yet fully understood. The implications of this asymmetry are enormous. What does it mean for us, human beings inhabiting this universe? The existence of more matter than antimatter is one of the deepest questions that physicists are trying to answer. In theory, if the universe had begun with equal amounts of both, they should have annihilated each other. Where is all the antimatter? This mystery leads us to question the very nature of matter and energy in the cosmos. But how does this translate into everyday life? When we look around, it seems that the universe is full of symmetry. Crystals, flowers, and many natural structures exhibit symmetrical patterns that are beautiful and harmonious. However, at a fundamental level, nature is more complex. Asymmetry reminds us that although the universe may appear balanced, there are hidden forces playing a crucial role in its functioning. A fascinating example of this asymmetry is found in particle physics, especially in the way fundamental force interactions are not always symmetrical. The weak interaction, which is responsible for processes like beta decay, is a clear example. Unlike gravity or electromagnetism, which maintain a more evident symmetry, the weak interaction breaks this norm. This peculiar behavior is a key piece of the puzzle that scientists are trying to solve. An intriguing aspect of symmetry violation is how it can influence the evolution of the universe. If we imagine the universe as a giant chessboard where each piece represents a particle, the way they move and interact is not the same everywhere. Some pieces behave more erratically, which can change the course of the game. This variability may be the key to understanding why the universe is the way it is and not otherwise. Scientific curiosity does not stop here. The search for answers about asymmetry has led to experiments in particle accelerators, where scientists attempt to recreate the conditions of the early universe. What would happen if we could observe how particles behave when colliding at high energies? The hope is that by doing so, we can unravel the mysteries of matter and antimatter and perhaps find answers to questions that have been on scientists' minds for decades. As we delve deeper into the study of asymmetry, it becomes evident that it is not just a physical phenomenon, but it also has philosophical repercussions. What does it mean for our understanding of the universe if the laws of nature are not symmetrical? It may lead us to question fundamental concepts of balance and justice in the cosmos. Science and philosophy often intersect in these debates, challenging our assumptions about reality. The history of asymmetry in physics also reflects the human journey toward knowledge. Each discovery about the asymmetrical nature of the universe brings us one step closer to a deeper understanding of our own existence. It shows us that, while we seek patterns and regularities, reality can be much more complicated than it seems. In summary, asymmetry in fundamental physics is not only a fascinating concept, but also essential for understanding the structure of the universe and the history of matter. It invites us to explore beyond what we see and to consider that, in the complexity of the cosmos, every irregularity may be a clue toward a more complete understanding. The journey to unravel these mysteries continues, and as we progress, it reminds us that human curiosity and the quest for knowledge are powerful forces in our exploration of the universe. In the vast and fascinating world of physics, the Standard Model stands as one of the most successful and robust theories we have developed to understand the fundamental particles that make up our universe. But what exactly is the Standard Model? Imagine a huge puzzle where each piece represents a subatomic particle. This model not only helps us identify the pieces, but also shows us how they fit together and how they interact. The central idea of the Standard Model is that despite the diversity of particles that exist, they all group into two main categories: fermions, which constitute matter, and bosons, which act as mediators of forces. It's as if we have a team of players, where some are the ones who score goals, while others are the coaches that allow the game to unfold. But here arises an intriguing question: why, in a universe that seems to function with such harmony, are there asymmetries that challenge our expectations? One fascinating aspect of the Standard Model is how it addresses symmetry. In theory, everything should be symmetrical, like a beautiful mirror reflecting the same image on both sides. However, reality is more complex. For example, in the case of fundamental interactions, symmetry can be broken. How is it possible that in a universe that seems governed by such precise laws, some particles behave differently from others? It's as if we have a card game where some cards always win, while others seem destined to lose. One of the most surprising examples of this symmetry breaking is found in particle physics, specifically in the violation of CP symmetry. In simple terms, this symmetry refers to the combination of two concepts: charge symmetry, C, and parity symmetry, P. What does this mean in practice? Imagine you are watching a magic show where everything seems to happen in a balanced way. But suddenly, a trick reveals that something doesn't fit. This is how CP symmetry violation works. It shows us that in the dance of particles, some act unexpectedly. The importance of this violation is not just a quirk of nature. It has profound implications for understanding our universe. Why is there more matter than antimatter? This is one of the most fundamental questions that scientists are trying to answer. In the Standard Model, it has been proposed that the observed asymmetry in the production of matter and antimatter could be related to the violation of CP symmetry. So, if at any point you have felt that matter has some sort of advantage over antimatter, you are not alone. Nature itself seems to have a preference. As we delve deeper into the Standard Model, it is crucial to mention the gauge bosons, which are the carriers of the fundamental forces. These are like messengers that carry information between particles. But what happens when these messengers are not equally effective? Interactions can become unbalanced, and this is where symmetry plays a vital role. It's as if we have a system in which some messengers always arrive on time, while others are delayed, thus altering the course of events. The mass of particles is also intrinsically related to symmetry. Through the Higgs mechanism, the Standard Model tells us how particles acquire mass. But what if I told you that this mechanism itself could be a source of symmetry breaking? The existence of the Higgs boson is a testament to this. It's as if the universe decided to grant some particles a weight that allows them to interact differently. However, this raises an intriguing question. Why does the Higgs boson have the mass that it does? The exploration of symmetry and asymmetry does not stop here. It also leads us to question the role of fundamental forces, electromagnetic, nuclear, and gravitational interactions are examples of how symmetry can be a common thread in understanding the laws of physics. But what happens when we try to unify these forces into a single theory? This is where the quest for unification becomes a monumental challenge. The Standard Model, while extremely successful, is not the whole story. There are aspects of the universe that we still do not fully understand, such as dark matter and dark energy, which are invisible yet essential components that influence the structure of the cosmos. What role do they play in the symmetry and asymmetry of the universe? These questions are the driving force behind modern research in physics. As we explore the complexity of the Standard Model, it becomes increasingly evident that asymmetry is not just a curiosity, but a fundamental characteristic of our universe. The way particles interact, the way symmetries are broken, reveals a cosmos full of surprises and mysteries. And so the quest to understand these interactions continues, guiding scientists toward new frontiers of knowledge. At the end of our journey through the Standard Model, the question persists. How can a system that seems so well structured and balanced harbor such asymmetries? The answer may lie at the very heart of nature, where symmetry and asymmetry coexist in a delicate balance. So, as we observe the universe, let us remember that in every corner there is a game of symmetry and asymmetry inviting us to keep exploring. What if I told you that at the heart of subatomic particles lies a profound mystery about symmetry and asymmetry that could change our understanding of the universe? Symmetry violation is a fascinating phenomenon that challenges traditional notions of balance and uniformity, and it is essential for understanding how nature operates at its most fundamental level. To begin, let's think about a board game. Imagine that on one side of the board all the pieces are the same color, but on the other side there is a mix of colors. This imbalance on the board could be similar to what happens in the world of particles. In certain interactions, what we would expect to be symmetric turns out to be asymmetric. This type of symmetry violation is not just a quirk of nature, it has profound implications for how particles are formed and behave. Particle physics tells us that there are fundamental forces that govern the behavior of the particles that make up everything we know. In an ideal world, we would expect interactions between particles to be perfectly symmetric. However, in the 1960s, scientists discovered that in the case of particles called quarks, symmetry is not respected. How is it possible for something as fundamental as symmetry to be broken in the subatomic world? A key example of this violation is CP symmetry, which combines two concepts: charge symmetry, C, and parity symmetry, P. Charge symmetry refers to the idea that if we swap particles for their antiparticles, there should be no difference in the interactions. On the other hand, parity symmetry relates to the idea that if we flip the universe, everything should look the same. But what happens when this symmetry is broken? Experiments have shown that certain interactions, such as those involving kaons, exhibit a clear violation of CP symmetry. This leads us to an intriguing question. Why is this violation of symmetry crucial for the very existence of the universe? The answer lies in the abundance of matter over antimatter in the Big Bang. It is expected that equal amounts of matter and antimatter were created. However, today we observe that the universe is composed almost exclusively of matter. This asymmetry is essential, as without it, the universe as we know it would not exist. In the laboratory, scientists have conducted experiments to observe this violation of symmetry. In the particle accelerator, for example, collisions are produced that allow researchers to study how particles behave under extreme conditions. Here, the asymmetric behavior of particles becomes a clue about the secrets of matter and energy. What does this tell us about the nature of reality? A useful analogy for understanding symmetry violation is to think of a balance scale. In a perfect balance, both sides are equal. But what if one side of the scale had extra weight? That scale would no longer be balanced, and that is exactly what happens in the universe. Symmetry violation shows us that there are different weights in the subatomic world that affect how matter and antimatter are distributed. Moreover, symmetry violation does not only occur in particle physics, it also extends to other areas of science. Cosmology, for example, faces fundamental questions about the evolution of the universe and the distribution of matter. In this sense, asymmetry plays a crucial role in the history of the cosmos, affecting everything from the formation of galaxies to the distribution of stars and planets. It is fascinating how science has tried to unravel these mysteries. As experiments advance and new theories develop, physicists continue to explore this uncharted territory. The quest for answers to complex questions about symmetry violation is a journey that not only leads us to understand the universe, but also to question our own existence within it. As we reflect on asymmetry in fundamental physics, it is essential to consider the implications of these findings for our understanding of the universe. It invites us to think beyond what we see and to question the very nature of reality. While symmetry may seem like a simple concept, its breaking in the subatomic world reveals an astonishing complexity that challenges our perceptions. So, as we look up at the stars and contemplate the vast cosmos, Let us remember that asymmetry is not just a physical phenomenon, but also a reminder of how extraordinary the universe we live in truly is. Every new piece of information we discover about symmetry violation brings us one step closer to understanding the very essence of existence. In this journey, curiosity and exploration are our best companions, guiding us through the mysteries of nature. Matter and antimatter are fascinating concepts in physics, but the curious thing is that despite both having emerged in equal amounts in the universe, there seems to be a notable difference. Why is there more matter than antimatter? This question leads us to explore one of the deepest mysteries of cosmology. First, it is essential to understand what matter and antimatter are. Matter is everything we can touch, see, and feel, from the air we breathe to the stars in the sky. On the other hand, antimatter is like a mirror of matter, composed of particles that have opposite charges. For example, the electron, a particle of matter, has a negative charge, while its counterpart in antimatter, the positron, has a positive charge. When matter and antimatter meet, they annihilate each other in an explosion of pure energy. This is a phenomenon that may seem straight out of a science fiction movie, but it is a reality in the world of physics. But then why, when looking at our universe, do we see a predominance of matter? The answer to this question may be related to something that happened in the early moments of the universe. After the Big Bang, the universe was an extremely hot and dense place, full of energy. In this environment, pairs of matter and antimatter particles were formed. However, something extraordinary happened at some point. It seems that more matter particles were produced than antimatter particles. This is known as baryon asymmetry, and it has intrigued scientists for decades. One possible explanation for this asymmetry could lie in a phenomenon called CP violation, which refers to how the laws of physics are not completely symmetrical when it comes to particles and their antiparticles. In simple terms, this means that the behavior of matter and antimatter is not exactly the same. To illustrate, imagine you have a game of bowling. If you throw a ball at the pins and knock some down, doing the same with a ball that has an opposite property may yield different results. Experiments in particle accelerators have shown that antimatter behaves slightly differently than matter, which could explain why matter has become dominant in the universe. But what implications does this have for us? If the universe were balanced in terms of matter and antimatter, life as we know it would not exist. The existence of more matter than antimatter allows for the formation of stars, planets, and eventually life. If everything were annihilated in a sea of energy, there would be no place for galaxies to form, nor even a place for atoms to join together to create the matter that makes up our world. Thus, the asymmetry between matter and antimatter is fundamental to the very existence of the universe as we know it. Scientists continue to investigate this issue through experiments that seek to create conditions similar to those of the early universe. By observing how particles interact, they hope to uncover clues about why there is more matter. Could there be some unknown property of matter that makes it prevail over antimatter? This is a question that lingers in the minds of many physicists. Let us imagine for a moment a universe where antimatter is more abundant than matter. In such a universe, stars would shine with opposite light, and chemistry itself could be radically different. Life, as we know it, might not exist. Reflecting on this, it becomes evident that the asymmetry in the universe is not a mere detail. It is a fundamental characteristic that has shaped our reality. As scientists develop new theories and experiments, the search for answers about matter and antimatter remains an exciting and active area of research. What will be the next discoveries that help us unravel this enigma? The possibilities are intriguing and will undoubtedly impact our understanding of the universe as a whole. In conclusion, the asymmetry between matter and antimatter is not just a physical phenomenon. It is one of the keys that allow us to exist. The quest for answers about why there is more matter than antimatter takes us on an adventure where each discovery opens new questions. Science in the end, is a continuous journey of exploration and wonder, and the mystery of matter and antimatter is just one of the many fascinating chapters in this story. The expansion of the universe is a fascinating concept that has captivated the curiosity of scientists and enthusiasts alike. But what does it really mean when we say that the universe is expanding? Imagine you are on an inflating balloon. As the balloon grows, the points drawn on its surface move away from each other. This is an intuitive way to think about how galaxies are moving apart in our vast universe. However, the expansion is not just a visual phenomenon. It has profound implications for the symmetry of the cosmos. Now, what relationship does this expansion have with symmetry? To understand it, it is essential to think about how the forces acting in the universe influence its structure. In a symmetric universe, we might expect that forces and matter would be distributed evenly, but the reality is that as the universe expands, asymmetries are introduced that affect how we see galaxies and how cosmic structures are formed. An intriguing point is how the expansion of the universe affects the light we receive from distant galaxies. When we observe a galaxy moving away from us, its light shifts toward the red, a phenomenon known as redshift. This effect not only indicates that the galaxy is moving away, but also shows that the very space between us and that galaxy is stretching. This is where the idea of asymmetry comes into play. The universe does not expand uniformly everywhere. Some regions may experience faster expansion than others, creating a complex tapestry of cosmic structures. The expansion of the universe also has implications for how we understand gravity. Gravity, which acts as a cosmic glue, does not behave the same way in an expanding universe. As galaxies move apart, the gravitational influence decreases, and this can lead to a series of unexpected phenomena. For example, some galaxies appear to be on the verge of separating from one another, prompting us to question our understanding of gravity and its relationship with expansion. What would happen if the universe stopped expanding? The answer to this question leads us to consider the ultimate fate of the cosmos. If the expansion were to halt, we could imagine a scenario where gravity began to dominate, causing galaxies to start attracting one another. This scenario could result in a collapsing universe where everything returns to a state of singularity. This cycle of expansion and contraction is known as the Big Crunch model and raises questions about the cyclical nature of time and the history of the universe. It is intriguing to think about how the expansion of the universe may influence the formation of the structures we observe today. Galaxies, clusters, and cosmic superstructures are not distributed evenly but form an elaborate web of filaments and voids. This uneven distribution is a direct manifestation of the asymmetry that arises from expansion. As the universe expands, dense regions tend to attract more matter, while less dense regions become voids, creating a pattern that challenges our notions of symmetry. The expansion also affects the distribution of dark matter, that mysterious substance we cannot see but whose presence is crucial for the formation of structures in the universe. Dark matter acts as a scaffolding, helping galaxies to cluster and form in the vast darkness of space. However, this interaction is not symmetric. Regions with a higher concentration of dark matter tend to attract more normal matter, further reinforcing the asymmetry in the structure of the universe. Another fascinating question is how the expansion of the universe affects life itself. As galaxies move away, the light that reaches us from them becomes dimmer. And in the distant future, we may live in a universe where many of the galaxies we see today will no longer be visible. This phenomenon raises questions about our place in the cosmos and how the asymmetry of expansion may influence the evolution of life on our own planet. Modern cosmology presents us with a constantly changing universe where expansion and asymmetry are integral parts of its nature. Yet despite the complexity of these concepts, there is a common thread: the search for patterns and the understanding of the forces that shape our cosmos. Each discovery reveals a new nuance in the history of the universe, and expansion becomes a phenomenon that not only alters structure but also invites us to question our perceptions of symmetry and asymmetry. Ultimately, the expansion of the universe is not just a physical matter, it is deeply intertwined with our own existence. It challenges us to think about time and space in ways we never imagined and reminds us that amidst the vastness of the cosmos, asymmetry can be both a challenge and an opportunity. By exploring these ideas, we embark on a journey toward understanding what it truly means to be alive in a universe that, although asymmetric, remains extraordinarily beautiful and mysterious. Gravity, that force that keeps us glued to the Earth and shapes our universe, has a fascinating role in the asymmetry of the cosmos. But do we really understand how gravity affects the structure of space-time? To unravel this mystery, it is first useful to think about how we perceive gravity in our everyday lives. When you drop a ball, you see it fall to the ground, but what would happen if we could see what occurs on a much larger scale? Imagine space as a large elastic sheet. When you place a heavy object like a bowling ball in the center of that sheet, the surface deforms. This deformation represents how gravity influences space-time. The greater the mass of the object, the greater the curvature produced around it. Thus, celestial bodies, like planets and stars, not only attract other objects due to their mass, but also distort the environment around them. And here arises an intriguing question: how does this curvature affect the formation of structures in the universe? The answer lies in the way gravity acts on matter, in the vast expanse of the cosmos. Gravity is the force that gathers matter, attracting gas, dust, and other elements. But it does not act uniformly. In some regions, gravity is more intense, which can result in the formation of galaxies and galaxy clusters. In others, gravity is weaker and can leave large voids. This uneven distribution of matter is a clear example of asymmetry in the universe. As matter groups together, it heats up and becomes stars, releasing light and energy. However, in this process, gravity can also bring a series of side effects. For example, when a star collapses at the end of its life, it can become a supernova, creating a black hole. These black holes are regions where gravity is so intense that nothing, not even light, can escape. The existence of black holes is another reminder of how gravity can create extreme asymmetries in space-time. It is interesting to note that gravity not only affects visible matter, it also plays a crucial role in dark matter, that mysterious substance that makes up a large part of the universe but that we cannot see. Dark matter interacts with gravity, helping to hold galaxies together. However, its asymmetric nature remains an enigma. Why is there so much dark matter in some regions and so little in others? This is a question that scientists are still trying to answer. The interaction between gravity and dark energy, another component that seems to be driving the accelerated expansion of the universe, adds another layer of complexity to cosmic asymmetry. Dark energy acts in opposition to gravity, pushing galaxies further apart from each other. This tug-of-war between gravity and dark energy is a fascinating example of how different forces can influence the structure of the universe in unexpected ways. But what about the way gravity affects time itself? Einstein's theory of relativity tells us that time is not constant and is affected by gravity. The closer you are to a massive object, the slower time passes compared to someone who is far from that mass. This phenomenon, known as gravitational time dilation, is one way that gravity introduces asymmetries in our perception of time and space. It is astonishing to think that, although we all experience gravity, the way it influences our environment can vary dramatically. In a black hole, time behaves in ways that challenge our usual understanding. This raises a fascinating question. How would the universe look if we could observe it from a place where gravity was different? The asymmetry in gravity not only affects the formation of cosmic structures but also has implications for the evolution of the universe. Dense regions of the cosmos can become places where new stars are born, while less dense areas may remain barren. This process of creation and destruction driven by gravity shapes the history of the universe and its future. Furthermore, gravity plays a central role in the interactions between celestial bodies. For example, the way planets orbit stars and how galaxies interact with each other is due to gravitational attraction. However, it is not always a harmonious dance. Sometimes galaxies collide and merge, creating new structures. This asymmetry in the movement of galaxies is a reminder that the universe is in constant change. As we explore more about how gravity influences the asymmetry of the universe, we realize that it is not just a matter of physical forces. There is also a philosophical component that invites us to reflect. The way gravity and matter interact raises questions about our place in the cosmos and the nature of reality itself. Gravity teaches us that although the universe is vast and full of beauty, it is also marked by asymmetry. This asymmetry is not a flaw, but an essential aspect of how the cosmos works. It challenges us to deepen our understanding and continue exploring the mysteries of the universe. Finally, when considering gravity and its relationship with asymmetry, a final reflection arises. The universe, in its complexity and diversity, invites us to marvel. Every star, every galaxy, and every cosmic structure is a testament to a fascinating journey, one in which gravity plays a fundamental role. And in this journey, asymmetry is not just a physical phenomenon, but an intrinsic part of the story we are called to discover. Cosmology is largely the story of the universe, from its birth to its evolution. But how do symmetry and asymmetry fit into this cosmic narrative? Symmetry in the universe suggests order and uniformity, while asymmetry introduces chaos and complexity. In this sense, symmetry is like the stage where the play unfolds, while asymmetry represents the actors that bring the plot to life. When observing the cosmos, one might wonder, why are galaxies, stars, and planets not distributed uniformly? The answer lies in the very nature of our reality. Think of a calm lake. When we throw a stone, waves are generated that propagate irregularly, creating patterns that are not symmetrical. This is how energy and matter are distributed in the universe. The expansion of the universe, which began with the Big Bang, has influenced this distribution, creating a complexity that challenges the notion of symmetry. A fascinating aspect of cosmology is how the laws of physics, which are fundamentally symmetrical, can lead to asymmetric outcomes. For example, if we consider gravity, which acts uniformly throughout space, we might ask, why does this force allow the formation of structures like galaxies and galaxy clusters? Gravity, by attracting matter, creates a cosmic dance that generates a clustering effect, contradicting the idea of a uniform and symmetrical distribution. Dark energy is another factor that adds a layer of asymmetry to the universe. This mysterious component, which seems to be driving the accelerated expansion of the cosmos, raises intriguing questions. How is it possible that something we cannot see is affecting the structure of the universe so significantly? Dark energy acts as a force pushing galaxies apart, creating an effect that defies expectations of symmetry. The standard cosmological model provides a guide to understanding how symmetry and asymmetry interact in the universe. This model, which describes the evolution of the universe from the Big Bang to the present, reveals that small fluctuations in matter density present at the moment of creation have led to the formation of large-scale structures that we observe today. This process, although governed by symmetrical principles, results in a cosmos where asymmetry abounds. Theories about cosmic inflation, which suggest that the universe underwent rapid expansion in its earliest moments, also illuminate the role of asymmetry. During this phase, small irregularities in energy density were amplified, leading to the variations we see in the distribution of galaxies. This raises another question. How can such a brief event have such lasting consequences on the structure of the universe? The answer lies in the fact that those small irregularities, as they expanded, became the building blocks of our cosmic reality. Symmetry and asymmetry also have profound implications for our understanding of matter and antimatter. In the observable universe, there seems to be an abundance of matter compared to antimatter. But why does this occur? Scientists believe that in the early moments of the universe, processes favored the creation of matter over antimatter, leading to the asymmetry we observe today. This phenomenon challenges our understanding of the fundamental laws of physics and leads us to question the nature of reality itself. But what does this mean for the future of the universe? As the cosmos continues to expand, asymmetry will continue to play a crucial role in its evolution. The formation of new stars and galaxies, the collapse of massive structures, and the creation of black holes are processes that depend on these asymmetric interactions. Thus, the universe becomes a dynamic and ever-changing stage where symmetry may be desirable, but asymmetry is essential for life as we know it. In this context, cosmological models must consider not only symmetry, but also asymmetry as an integral component of the evolution of the universe. As scientists advance in their understanding of dark matter and dark energy, new questions arise about how these elements affect symmetry and asymmetry in the cosmos. The quest for answers to these questions is fundamental to unraveling the mysteries of the universe. In summary, the relationship between symmetry and asymmetry in cosmology is a fascinating aspect of our exploration of the universe. Each discovery brings us a little closer to understanding how the forces that govern the cosmos shape the reality we inhabit. As we continue to investigate, new theories and concepts are likely to emerge that will help us unravel this cosmic enigma, revealing the beauty and complexity of a universe that is at once both symmetrical and asymmetrical. And who knows, perhaps at the end of this journey we will discover that the true essence of the universe lies in the dance between order and chaos, between symmetry and asymmetry. The theory of cosmic inflation is one of the most fascinating ideas that have emerged in modern cosmology. Why, you may ask? Because it offers us a radical explanation of how our universe began and at the same time helps us understand some of the asymmetries we observe in it. But what exactly is this inflation, and how does it relate to symmetry and asymmetry? First, let's think about how the universe developed. In the beginning, everything was compressed into an extremely dense and hot point. In an instant, something extraordinary happened. This point began to expand at an impressive speed in a very short span of time. Much shorter than a blink, the universe expanded exponentially. This inflationary phase caused small irregularities in the density of the universe to be amplified, giving rise to the structure we see today. But why is this rapid expansion important, and how does it relate to symmetry? Here is where the story becomes intriguing. When we refer to symmetry, we talk about uniformity and balance. In a symmetric universe, we might expect all regions of space to be equal, without fluctuations or irregularities. However, cosmic inflation introduced variations that, although small, became the foundations of galaxies, stars, and ultimately, life as we know it. So instead of a perfectly symmetric universe, we have a cosmos filled with asymmetries that shape everything we see. Imagine you are inflating a balloon. At first, the balloon is small and compact, but as you blow into it, it starts to grow disproportionately in some areas. Some parts expand more than others, creating bulges and wrinkles. In this sense, our reality resembles that balloon. The small differences in density during cosmic inflation translated into a universe full of complex structures. Why are these small variations so significant? Each of these irregularities became the seedbed for future cosmic structures. Areas where the density was slightly higher attracted more matter, forming galaxies and clusters of galaxies. Therefore, those initial asymmetries, which might seem like disadvantages in an ideally symmetric universe, turned out to be the keys to the formation of everything we know. Isn't it fascinating to think that the diversity of the universe comes from small imperfections? But inflation is not just about creating structures. It also shows us how these asymmetries can affect the fate of the universe. As the universe expanded, the laws of physics began to play a crucial role. Gravity, which acts asymmetrically, started to dominate the dynamics of the cosmos. Denser regions of matter began to attract other particles, while less dense areas expanded more rapidly. How can we understand this interplay between gravity and expansion? This tug-of-war between gravity and expansion is fundamental to the evolution of the universe. As inflation stopped, the universe ceased to expand rapidly and began to cool and expand at a more controlled rate. However, the traces of that inflationary phase are still visible in the large-scale structure of the cosmos. But what about symmetry in all of this? Could there be a balance between the forces that govern the universe? Here is where more intriguing questions arise. The theory of inflation also suggests that the universe could have split into multiple regions, each with its own physical laws. This implies that although we live in a universe that seems to follow certain rules, there could be other universes, or multiverses, with different properties. What does this mean for our understanding of symmetry and asymmetry? The concept of the multiverse introduces a new level of complexity. If the universe we know is just a bubble in an ocean of universes, then symmetry could be just one of many possibilities. Perhaps in another universe, the laws of physics are completely different and the asymmetry we observe here does not apply. Could there be a universe where matter and antimatter exist in perfect symmetry? As we advance in our understanding of cosmic inflation, we also face new questions about the very nature of reality. How can we reconcile the absence of symmetry in our universe with the search for an underlying order? Cosmic inflation not only offers us a window into our past, but also challenges us to reconsider what we know about the structure of the cosmos. All of this raises profound reflections on the very nature of the universe. The asymmetry that surrounds us, far from being an inconvenience, may be an essential feature that allows for the existence of life. Through inflation, we learn that what might seem like chaos is, in fact, a dance of forces and energies that have shaped everything we know. Isn't the beauty of the asymmetric what makes the universe so extraordinary? The theory of inflation reminds us that despite the irregularities, the universe has a rich and complex history. From its beginnings to its current expansion, each step has been crucial for creating an environment where life can flourish. The next time you look at the stars, think about the asymmetries that have led to the formation of those bright points in the sky. Isn't it amazing to think that it all began with an inflationary explosion and a play of symmetries and asymmetries? What really composes our universe? One of the great questions that scientists have tried to answer is, what is dark matter and dark energy, and how do they affect the symmetry of the cosmos? To address this issue, we need to think of the universe as a vast ocean where the matter we see, like stars and planets, is just the surface, while the true essence of this ocean is hidden beneath the surface in forms we cannot see or touch. Dark matter is a kind of ghostly material. Although it does not emit light or energy, we know it is there because of the effects it has on visible matter. Imagine a dance in a dark room. You cannot see all the dancers, but you can feel how they move and how their movements affect those you can see. This is how scientists detect dark matter, by its gravitational influence on galaxies and other structures in the universe. But why is dark matter important for the symmetry of the universe? The answer lies in how it influences the distribution of matter. If dark matter did not exist, galaxies would not have enough gravity to hold together. This creates an imbalance, an asymmetry in the way matter is distributed in the universe. Without dark matter, the cosmos might look very different, with galaxies scattered in an irregular and chaotic manner. Dark energy, on the other hand, is even more enigmatic. This mysterious force seems to be driving the accelerated expansion of the universe. It's as if the universe is in a race, and dark energy is the fuel that propels it to increase its speed. But what does this mean for symmetry? The accelerated expansion introduces a temporal asymmetry, as the structures of the universe are moving away from each other at a rate that changes over time. In this sense, dark energy could be seen as an agent of perpetual change, creating a cosmos in constant transformation. Now, it might seem that dark matter and dark energy are opposites, but in reality, they work together in the grand design of the universe. While dark matter tends to attract and group, dark energy pushes and separates. This interaction creates a delicate balance, a dance between attraction and repulsion that shapes our cosmos. However, this balance is not perfect. The asymmetry introduced by both components suggests that there are forces at play that we do not yet fully understand. It is fascinating to think that although we cannot see or touch dark matter and dark energy, their existence is fundamental to the structure of the universe. Most of the matter in the cosmos is dark. In fact, it is estimated to account for about 95% of all matter and energy. This fact highlights how little we truly know about what composes our universe. The symmetry we observe in cosmic structures may be just an illusion, as most of what we see is only a small fraction of reality. The search for dark matter and dark energy has led scientists to develop new theories and innovative experiments. From telescopes that observe the sky in invisible wavelengths to particle accelerators that attempt to recreate the conditions of the early universe. Each discovery is a step toward understanding how these forces influence the symmetry and asymmetry of the universe. But the question remains, will we ever fully unravel the secrets of dark matter and dark energy? What is even more intriguing is how these forces might be related to life on Earth. The asymmetry in the universe, which manifests in the way matter and energy are distributed, may have played a crucial role in creating the right conditions for life. If the universe were completely symmetrical, we might never have existed, as life as we know it may depend on those small asymmetries that allow for diversity and complexity. Human perception is also affected by these concepts of symmetry and asymmetry. In our daily lives, we are accustomed to seeing patterns and balances in everything around us, from the architecture of a building to the composition of a work of art. However, the universe teaches us that beauty can also be found in imperfection and imbalance. This reflection on asymmetry can help us appreciate not only the cosmos but also our own existence. As we advance in our understanding of the universe, it is crucial to keep an open mind to new ideas and possibilities. Dark matter and dark energy are just two of the many mysteries that await us, and each discovery can change our perception of symmetry and asymmetry in the cosmos. Science is constantly evolving, and what seems incomprehensible today could be the foundation of new theories in the future. Finally, the exploration of dark matter and dark energy underscores the importance of human curiosity. It drives us to ask questions, to investigate, and to seek answers in the depths of the universe. As we continue this quest, we may discover that the true nature of the cosmos is much richer and more complex than we ever imagined. Who knows what other secrets lie hidden in the vastness of space? The story of the universe, with all its asymmetries and mysteries, is far from complete. So the next time you look up at the starry sky, remember that what you see is just a part of a much larger story. String theory is a fascinating approach that has revolutionized our understanding of the universe. But what exactly is this theory, and how does it relate to symmetry and asymmetry? To understand it, we must first travel to a world where particles, which in our traditional view are the building blocks of matter, become vibrating strings. Instead of thinking of electrons and quarks as tiny spheres, imagine them as small strings that vibrate in different ways. How does this relate to symmetry? The key lies in the vibrations of these strings. Each mode of vibration corresponds to a different particle, just as the strings of a guitar can produce different musical notes depending on how they are played. The strings of the theory vibrate in ways that give rise to various particles. But here is where it gets interesting. The way these strings interact with each other can reveal patterns of symmetry and asymmetry. Let's consider a simple example. Think about how a group of dancers can move in perfect synchrony, creating a beautiful choreography. This coordinated movement represents symmetry. However, if one of the dancers decides to do something different, like an unexpected turn that introduces asymmetry into the dance. In string theory, the interactions between the strings can be similar to this dance, where some vibrations may be perfectly symmetrical, while others may break this harmony. Now let's consider an intriguing concept: additional dimensions. String theory suggests that in addition to the three spatial dimensions and time that we know, there are additional dimensions that are curled up or compacted in ways that we cannot see or directly experience. Doesn't that sound a bit strange? As we explore these additional dimensions, it becomes evident that symmetry plays a fundamental role in how these dimensions are organized and behave. But what does this mean for asymmetry in our universe? One of the big questions in physics is why there is more matter than antimatter. This difference may be related to the symmetry properties of the strings. If interactions at this fundamental level were not perfectly symmetrical, it could have allowed matter to prevail over antimatter. Imagine that these strings, by vibrating in different ways, create conditions that favor the existence of what we know as matter. As we delve deeper into string theory, we find that it also offers a way to unify the fundamental forces of nature. Strings may be the thread that ties together gravity, electromagnetism, and nuclear interactions. If we can understand how these strings work and how they relate to each other, we might uncover an underlying symmetry that connects all the forces in the universe. Wouldn't it be amazing to find a single explanation for all physical phenomena? However, string theory is not without its challenges. We are still in the process of investigating and testing its implications. Imagine us as explorers in a vast ocean of knowledge, trying to unravel the mysteries of strings. Each discovery may lead us to new questions and a deeper understanding of symmetry and asymmetry in the universe. As we progress in this exploration, the idea that symmetry is not just an aesthetic property, but a fundamental principle that guides the structure of the cosmos becomes increasingly clear. Think about how symmetry manifests in nature. From the wings of a butterfly to the structure of a galaxy, string theory suggests that this symmetry extends even to dimensions we cannot see. But what about entropy? Entropy, which is a measure of disorder in a system, is also related to symmetry. As the universe evolves, entropy tends to increase, introducing a form of asymmetry in time. In this context, string theory could offer new perspectives on how symmetry and asymmetry intertwine in the history of the universe. As we continue to explore string theory, we encounter the possibility that our ideas about symmetry and asymmetry may change. Perhaps what we consider asymmetric in our universe is merely a manifestation of more complex patterns that we have yet to understand. What surprises does the future hold in our quest for answers? In this journey, string theory becomes a bridge between what we know and what is yet to be discovered. It invites us to reflect on how the vibrations of these strings not only shape matter and energy, but may also reveal the very nature of reality. Symmetry and asymmetry are interconnected in ways we are still trying to unravel. In the end, string theory reminds us that the universe is a place full of mystery and beauty. Symmetry may be a guide, but asymmetry is where we find the most fascinating stories. Each discovery in this field not only brings us closer to understanding the cosmos, but also invites us to marvel at the complexity of existence. So, as we explore the strings and their vibrations, let us remember that every open question is an opportunity to continue learning about the universe we inhabit. Symmetry and asymmetry are concepts that are deeply intertwined in the fabric of the universe. And one of the most intriguing places where these concepts play a crucial role is in entropy and the second law of thermodynamics. Why does time seem to flow in one direction? What does this have to do with entropy? These are some of the mysteries we will explore in this section. In simple terms, entropy can be understood as a measure of disorder. When we observe a messy room as if it has been invaded by a tornado of clothes, toys, and scattered objects, we can say it has high entropy. In contrast, an orderly room where everything is in its place has low entropy. But why does it seem that the universe always moves toward disorder? This leads us to the second law of thermodynamics, which states that in a closed system, entropy tends to increase over time. But what does this mean in terms of our universe? Imagine that the universe is like a huge clock that, instead of ticking uniformly, moves from an ordered state to a disordered one. As time progresses, particles move, collide, and combine, creating increasing chaos. This process of transitioning from order to disorder is one of the reasons why time has a direction. And if you think about it, the arrow of time is deeply connected to entropy. Now, the question that arises is, why did the universe start in a state of low entropy? The answer to this relates to the Big Bang. In its early stages, the universe was extremely concentrated, meaning it had low entropy. Over time, as the universe expanded, entropy began to increase, leading to the diversity and complexity we observe today. This increase in entropy is related to the asymmetry in the way forces and particles interact. But what about the relationship between entropy and life? This is where the story becomes even more fascinating. Life, as we know it, seems to defy the increase of entropy. Living beings, by growing and developing, create order in their internal structures. However, this order does not contradict the second law of thermodynamics. In reality, organisms absorb energy from their surroundings, transforming ordered energy into disordered energy and increasing the total entropy of the universe. So, although we may seem orderly, we are contributing to the overall trend toward disorder. As we reflect on how entropy influences the universe, another intriguing question arises: what will happen in the future? As the universe continues to expand, entropy will keep increasing. Does this mean we will eventually reach a state where everything is homogeneous and disordered? Some scientists suggest that we could reach a state known as heat death, where all stars will have extinguished and the universe will be a cold, dark place filled with scattered particles. However, this distant future is full of uncertainties. Could there be cosmic events that alter this path toward increasing entropy? Gravity, for example, plays a fundamental role in organizing matter into structures like galaxies and stars. As gravity acts on matter, it can create areas of low entropy amidst an expanding universe. Entropy is also related to information. In the world of physics, information is considered a form of order. As we increase our understanding of the universe, we are creating a sense of order from chaos. But what happens when information is lost? If entropy continues to increase and information disperses, we could face a universe that becomes increasingly difficult to understand. All of this leads us to reflect on the role that entropy plays in our own existence and in the pursuit of knowledge. As we delve into the mysteries of the cosmos, it is crucial to understand that asymmetry and entropy are part of a complex dance that has shaped everything we know. Life, time, and the universe are intertwined in a narrative that challenges our notions of order and chaos. Ultimately, entropy offers us a unique perspective on the nature of time and reality. In a universe where asymmetry and disorder are inevitable, the pursuit of knowledge and understanding becomes an act of resistance against increasing entropy. It reminds us that despite the forces that tend to pull us toward chaos, there is beauty and meaning in the order we can create and in the knowledge we can attain. So the next time you think about time and the universe, remember that entropy and asymmetry are forces that shape our existence. In this journey through the cosmos, every discovery we make is a small triumph over the inherent disorder of the universe, and thus, the story of asymmetry and entropy becomes a story of life, struggle, and hope amid cosmic chaos. Asymmetry in the universe is not only a fascinating concept, but it is also a fundamental pillar that has allowed the existence of life as we know it. But how is it possible that a universe full of imbalances and differences has given us the opportunity to exist? To understand this relationship, we must explore how asymmetry manifests in nature and its connection to the emergence of life. When we look around, we find symmetry in many aspects of nature: the petals of a flower, the wings of a butterfly. Even crystal structures exhibit symmetrical patterns. However, at the heart of these patterns, in the essence of life itself, we find a complex network of asymmetries. Why then has life developed in a universe that seems so inclined toward disproportion? The answer lies in the fact that asymmetry can be a source of diversity and complexity. In a symmetrical world, opportunities for innovation and adaptation would be limited. Imagine a calm ocean where each wave is identical to the previous one. In contrast, a turbulent sea filled with waves of different sizes and shapes offers us a rich variety of ecosystems and opportunities. Similarly, the asymmetry in the universe has allowed for the evolution of diverse organisms, each adapted to its particular environment. But what role does asymmetry play in biological processes? An intriguing example is chirality, a phenomenon that manifests in molecules. Most biological molecules, such as amino acids and sugars, are chiral, meaning they exist in forms that are mirror images of each other. This asymmetry in the nature of molecules has been crucial for the formation of proteins and nucleic acids, the building blocks of life. If the universe had been completely symmetrical, life may never have found its way. Imagine a universe where chemistry is completely symmetrical. In that world, the basic components of life would be unable to interact in the way they do in our universe. The diversity of life forms we see on Earth would likely not exist. Asymmetry, in a way, acts as the engine of biological diversity, allowing different species and ecosystems to emerge. Moreover, asymmetry is also reflected in evolution itself. Natural selection, which drives evolution, is based on variability. This process requires differences among organisms so that some can adapt better to their environment than others. Without asymmetry, living conditions would be uniform, and evolution as we know it could not occur. Every small imbalance in the environment can lead to new adaptations and eventually to new species. As we reflect on the connection between asymmetry and life, we can observe that even catastrophic events have played a crucial role in this dynamic. For example, Mass extinctions, although devastating, have allowed new forms of life to emerge and dominate. The asymmetry in the history of the planet has been, in many ways, a facilitator of change and transformation. However, we should not limit our reflection on asymmetry to biology. In the social and cultural realm, diversity also flourishes amid asymmetry. In music, art, and literature, it is the variety of experiences, emotions, and perspectives that enrich our understanding of the world. Asymmetry teaches us that life does not need to be perfect or uniform to be beautiful and meaningful. So, what does this imply for our understanding of the universe? Asymmetry invites us to reconsider our expectations of perfection and order. It reminds us that often it is in disorder and diversity that we find true beauty and potential. Life, in its purest essence, thrives on difference. The pursuit of symmetry, while important, should not overshadow the appreciation of asymmetry. Nature has found ingenious ways to use asymmetry to create a vibrant and dynamic world. Thus, every time we look around, we should remember that the diversity of life, with all its complexities and nuances, is a testament to the value of the asymmetric. In conclusion, asymmetry is not just a physical concept, but a vital force that has shaped existence in our universe. From the molecules that make up our biological structure to the cultures that enrich our lives, asymmetry offers us a kaleidoscope of possibilities. Thus, every corner of our world, every living being, is a reflection of the dance between symmetry and asymmetry, a dance that ultimately defines us as beings in an extraordinary universe. Symmetry is not only present in nature and the laws of physics, it also manifests in art, architecture, and even in our everyday lives. But what role do symmetry and its opposite, asymmetry, play in human culture? Let's delve into this fascinating connection. Symmetry has been a fundamental concept in art since time immemorial. When we observe masterpieces of painting, sculpture, or architecture, we notice that many of them consist of symmetrical elements. This is because symmetry is often perceived as attractive and harmonious. Why are we drawn to the symmetrical? One possible explanation is that our minds seek patterns and order in the world around us. Symmetry can offer a sense of stability and balance, something that can be comforting in an often chaotic world. In contrast, asymmetry has also found its place in art. Many modern artistic movements, such as cubism or abstract art, play with the idea of asymmetry to challenge our perceptions and make us question what we consider beautiful. Can asymmetry also be a form of beauty, just as in nature, where asymmetry can reflect diversity and adaptation? In art, it can symbolize originality and innovation. It invites us to see the world from a new perspective. Philosophy has also been influenced by these concepts. Since ancient Greece, thinkers like Plato and Aristotle discussed the idea of symmetry and proportion in relation to beauty and truth. But what happens when symmetry is altered? Many contemporary philosophical currents have explored the notion that disorder and asymmetry can be equally valid in the pursuit of knowledge and understanding of existence. This opens a new field of reflection. Can asymmetry offer a deeper insight into reality? In literature, symmetry and asymmetry also play a crucial role. Symmetrical plots, where events reflect or invert each other, can provide a sense of closure and resolution. But what about stories that are asymmetrical, where the conflict does not resolve predictably? These narratives can be more intriguing as they reflect the complexity and uncertainty of life. In this sense, literature can be a mirror of reality, where asymmetry becomes a tool to explore human emotions. In music, symmetry and asymmetry also have their place. Many classical compositions are based on symmetrical structures, creating melodies that resonate with our emotions. However, more experimental genres play with dissonance and irregularity, taking us on an unexpected sonic journey. Isn't it fascinating how music can evoke different feelings through these contrasts? Often, it is the asymmetry in music that provokes a more intense emotional response. Architecture, for its part, reflects the duality of symmetry and asymmetry in a very tangible way. From the pyramids of Egypt, which embody perfect symmetry, to the works of modern architects who play with unusual and asymmetrical forms, the way we build our spaces speaks to our relationship with the environment. What kind of message do we want to send with our buildings? Symmetry can suggest stability and permanence, while asymmetry can evoke movement and change. In the realm of fashion, symmetry is a key element in creating visually appealing garments. However, asymmetry has gained ground in contemporary trends, challenging norms and allowing individuals to express themselves in unique ways. How does this influence our personal perception and identity? Fashion thus becomes a playground where symmetry and asymmetry coexist, reflecting the diversity of life itself. Cinema, on the other hand, uses visual symmetry and asymmetry to tell stories effectively. Many films employ symmetrical framing to convey order, while asymmetrical scenes can create tension and drama. Isn't it interesting how a simple aesthetic decision can transform the narrative of a film? The way the story is presented can influence our emotions and how we interpret events. Finally, dance and movement also draw from these concepts. Choreographies that play with symmetry can be visually stunning, but those that incorporate asymmetry can be more emotive and expressive. Is it not in imperfection that we find the true essence of being human? When observing dance, we can see how balance and imbalance intertwine, creating a unique experience that touches our emotions. In summary, symmetry and asymmetry are not just abstract concepts, they are forces that shape our culture and our understanding of the world. They offer us different ways to perceive beauty, truth, and existence. As we explore these ideas in our daily lives, we can begin to appreciate the complexity and richness of the human experience. In a universe that is inherently asymmetrical, perhaps it is that very asymmetry that allows us to find meaning and connection in our reality. The search for unification in physics is like trying to assemble a giant puzzle where each piece represents one of the fundamental forces we know: gravity, electromagnetism, and the weak and strong nuclear forces. Have you ever wondered what would happen if all these forces could connect in a single theory? Scientists are on this constant quest, trying to find that common thread that unifies all the interactions of the universe. To understand why this is so important, let's think about how we interact with the world. When we throw a ball, we are witnessing gravity in action, but at the same time, if we turn on a light bulb, we are experiencing electromagnetism. However, at the smallest scale, subatomic particles are also subject to nuclear forces. How is it possible that all these forces, which seem so distinct, have a common root? The idea of symmetry plays a crucial role in this search. Imagine an equilateral triangle where all three sides are identical. This shape is symmetrical. Similarly, physicists believe that by finding a unified theory, all fundamental forces should be described by a set of symmetrical principles. But here lies the dilemma. In the universe, we have observed that there are asymmetries. Why then does a world that seems governed by symmetry present so many irregularities? String theory is one of the most promising approaches in this regard. This theory suggests that particles are not points, but rather vibrating strings. Each vibration of the string corresponds to a different particle. But here comes the fascinating part. In this vibration, the strings can adopt different shapes and dimensions, introducing the possibility of understanding symmetry in a completely new way. What if, in the fundamental structure of the universe, all forces were connected through these strings? However, it is not an easy task. Physicists face a monumental challenge, finding evidence to support string theory and other unified theories. How do you prove something that lies beyond our capacity for direct observation? This is one of the great questions that haunts the scientific community. The particles and forces we are trying to understand are often in the realm of the infinitely small, making their study difficult. Symmetry also offers us a powerful tool to tackle this challenge. By searching for patterns in data and in particle interactions, scientists can identify the rules that govern the universe. But what happens when we find violations of these symmetries? This is where the creativity of scientists comes into play. Every time an asymmetry is discovered, it opens the door to new theories and questions. Could this asymmetry be a clue that helps us understand how to unify the forces? One of the most intriguing examples of this search lies in the study of the interaction between gravity and quantum theory. In the quantum world, things do not always behave as we expect. Particles can exist in multiple states at the same time, and gravity, in turn, seems to be a force that acts differently. Is it possible that gravity, due to its nature, is separate from the other fundamental forces, or could there be some underlying symmetry that we have yet to discover? Some scientists suggest that by better understanding symmetry and asymmetry in fundamental forces, we could get closer to a theory of everything that explains how the universe works as a whole. This theory would not only be a major breakthrough in physics, but it could also have profound implications for our understanding of reality itself. Are we one step away from discovering the rules that govern everything we know? The unification of forces also has a philosophical flavor. If we manage to understand how all fundamental forces intertwine, we might be closer to answering existential questions about our place in the cosmos. What does it mean to be part of this vast universe? Are we alone in it? The search for answers to these questions could lead us to a new understanding of life and the universe. The exploration of symmetry and asymmetry in fundamental physics is ultimately a reflection on the nature of human knowledge. Each discovery, each violation of symmetry pushes us to rethink what we know and what we believe we know. Science advances step by step, but each step is a testament to human ingenuity and our capacity to question and explore. In this sense, the search for unification is not just a scientific endeavor, but also a journey of personal discovery. As we delve into the mysteries of the universe, we find ourselves in the process. Curiosity drives us, and every question we ask is an invitation to explore beyond the known. What new revelations await us on the horizon of physics? That is the excitement of being part of this endless quest. Thus, as we look to the future, symmetry and asymmetry teach us that the universe is a place full of surprises, a place where what seems chaotic may be governed by an underlying order that we are still trying to unravel. What discoveries does the future hold for us? The answer lies in the path we choose to walk together in this fascinating adventure of understanding the cosmos. Asymmetry in the universe is not just a physical phenomenon, it also raises profound philosophical questions. What does it really mean for the universe to be asymmetric? This simple question becomes a labyrinth of reflections on our existence. The very nature of reality seems to be at stake. If symmetry represents balance and harmony, what does asymmetry reveal about us, about the cosmos, and about our place within it? Let's consider the idea of life itself. Evolution has emerged in an environment that is not perfectly symmetrical. Life is diverse and complex, but it often relies on asymmetric patterns. Could it be that asymmetry is a source of creativity and adaptation? Observing how species evolve and adapt to their environment, it is fascinating to think that the lack of symmetry can be a driving force for innovation and change. In this sense, asymmetry is not just a limitation, but also an opportunity. Think about the way humans perceive the world. Our minds are designed to find patterns and symmetries in our daily experience. However, life is full of surprises and disorder. How does this influence our understanding of reality? Asymmetry challenges us to step out of our comfort zone. It forces us to question our beliefs and to explore the chaos that often lies at the heart of life. There may not always be a clear answer, but it is precisely in uncertainty that the beauty of existence resides. Philosophy has also been impacted by asymmetry. Great thinkers have reflected on the concept of order and chaos. The idea that the universe is inherently asymmetric has led many to question whether there is a purpose behind this arrangement. Is chaos a manifestation of divine creativity, or is it simply a consequence of physical laws? The search for answers pushes us to deepen our understanding of nature and at the same time confront our own beliefs. Asymmetry also raises questions about morality and ethics. If the universe is not balanced, how can we define what is good and bad? The decisions we make are often influenced by a sense of moral symmetry. However, reality is more complicated. Could it be that by accepting asymmetry in the universe, we must also accept complexity in our ethical decisions? Morality may not be a straight line, but a landscape full of nuances, where decisions are not always clear. In the realm of science, asymmetry leads us to question the future of the universe. With the expansion of the cosmos and dark energy, we face the possibility of a universe in constant change and evolution. What implications does this have for our understanding of time and space? The asymmetry in the expansion of the universe may suggest that the fate of the cosmos is far from predictable. It invites us to imagine a future where reality unfolds in unexpected ways. The search for unification in physics is also affected by asymmetry. Theories that attempt to bring together the fundamental forces of the universe must grapple with this complexity. Could it be that asymmetry is an obstacle, or perhaps a pathway to a deeper understanding of reality? Science progresses as we face these challenges, and each discovery opens new doors to even more intriguing questions. In art and culture, asymmetry has been a source of inspiration. From music to painting, irregularity and imbalance have led to the creation of masterpieces. What does this tell us about our aesthetic perception? Perhaps asymmetry in art reflects the diversity and richness of the human experience. It reminds us that beauty can arise from chaos and that the imperfect often resonates more deeply with our emotions. The implications of asymmetry in our daily lives are undeniable. We often seek stability and order, but reality presents us with a tapestry of asymmetries. How do we respond to this? By embracing the complexity and disorder of life, we may find new ways of resilience. Asymmetry can teach us to adapt and grow amidst uncertainty. As we reflect on asymmetry, we must also consider its role in our connection to the universe. Science and philosophy provide us with tools to explore these questions, but the answer is ultimately personal. What does asymmetry mean to you in your life? The search for truth can be a solitary path, but each step brings us a little closer to understanding the complexity of our existence. Asymmetry, therefore, is not just an aspect of the universe. It is a mirror that reflects our own humanity. It reminds us that while we seek clarity and symmetry, we often find meaning in chaos. In this journey of exploration, we may discover that asymmetry is, ultimately, an essential part of the universe's story and our own. How will you choose to see the world through this lens? The answer may be as asymmetric as the universe itself. In the vast universe of scientific research, there is a topic that stands out for its complexity and relevance: the study of symmetry and asymmetry. But what are the questions that truly drive us to delve deeper into this field? What mysteries remain unresolved about how the universe works? The search for symmetry in physics resembles a puzzle that, once completed, could reveal surprising truths about our existence. Current research focuses on unraveling the secrets of dark matter and dark energy. Although we cannot see these components, we know they make up most of the universe. Why is it so crucial to understand their nature? Because by doing so, we might discover why the universe behaves the way it does. Imagine a world where the laws of physics operate differently. What implications would that have for our understanding of the cosmos? Another area of interest is the study of neutrinos, elusive particles that have taught us about symmetry violation. Why are these tiny particles so difficult to detect? As scientists conduct more advanced experiments, the question of how they influence matter and antimatter becomes increasingly intriguing. The answer may be hidden in a dark corner of the universe, waiting to be discovered. Particle physics is also in the spotlight. With the Large Hadron Collider, researchers are seeking answers to fundamental questions about the structure of the universe. What happens when particles collide at speeds close to the speed of light? Could this energy reveal unknown forms of asymmetry? The possibility that we are one step away from understanding fundamental interactions is exciting, but it also raises more questions. In the realm of cosmology, current models suggest that the expansion of the universe may be related to symmetry. How does this affect the way we see our place in the cosmos? As the universe expands, so do our questions about its origin and future. The search for symmetry leads us to question whether the universe has always been in a state of equilibrium, or whether, on the contrary, it has been on a journey of asymmetry from the beginning. String theory, a concept that has captured the imagination of many, also plays an important role in this quest. What if additional dimensions could provide an answer to the asymmetry we observe? As scientists delve deeper into these ideas, a new world of possibilities opens up that challenges our current understanding of physics. Entropy is another captivating concept that offers clues about asymmetry in time. How does entropy influence the development of the universe and life itself? The idea that disorder and lack of symmetry are fundamental to the evolution of the cosmos is fascinating, and exploring this link may lead us to a deeper understanding of our own existence. Life itself is a phenomenon that might not have been possible without the asymmetry of the universe. What role does asymmetry play in the evolution of species and the diversity of life on Earth? Reflecting on these questions, it is evident that symmetry and asymmetry are more than abstract concepts. They are the foundations upon which life is built. The philosophical implications of asymmetry are also worth mentioning. If the universe is intrinsically unbalanced, what does that mean for our understanding of reality? Asymmetry may suggest that life and consciousness are ultimately products of a chaotic environment. This perspective can challenge our beliefs about order and structure in the universe. As we advance in these investigations, we also find ourselves at the intersection of science and philosophy. How can new theories about symmetry and asymmetry influence our worldview? Science is not just about facts and figures. It is about the search for meaning in a universe that often seems chaotic and disordered. Looking to the future, the exploration of symmetry and asymmetry will continue to be a fertile field for research. What discoveries await us in the coming decades? The combination of theoretical physics and practical experiments promises to reveal secrets of the universe that we cannot yet imagine. Perhaps by piecing together this puzzle, we will find answers to the deepest questions about our existence. The history of science is full of surprises, and the quest for symmetry and asymmetry is no exception. Each advance pushes us to question what we thought we knew and to open ourselves to new possibilities. As we continue this journey, it is essential to maintain curiosity and an open mind, as the universe always has more surprises in store for those who dare to explore. The next time you look up at the starry sky, remember that each star and each galaxy is part of an intricate tapestry of symmetries and asymmetries. Each discovery in this field brings us a little closer to understanding not only the universe but also ourselves. The question that remains is, what discoveries would you like to see in the future? Science is always evolving, and you could be part of that story. Symmetry has been a fascinating concept throughout history, not only in physics, but also in our everyday lives. As we reach the end of this journey, it is important to reflect on what we have learned and how the asymmetry in the universe helps us better understand our existence. Why does the universe seem to be full of surprises and imbalances? The answer lies in the fact that asymmetry is not just a physical phenomenon, but also an integral part of our reality. Let's think about arts. Many of the most impactful works are not symmetrical. Asymmetry can draw our attention and evoke our emotions, just as the universe attracts us with its mysteries. When we observe the cosmos, we notice that symmetry and asymmetry coexist, creating a dynamic balance. What would happen if everything were perfectly symmetrical? Perhaps the universe would be monotonous, lacking the contrasts that make life so rich and complex. The diversity we see in the world, from the shapes of flowers to the structure of galaxies, is a testament to how asymmetry can give rise to beauty. The quest to understand the asymmetries of the universe leads us to question our own existence. If there is more matter than antimatter, what does that mean for us? The answer may be related to the delicate balance that has been established since the early moments of the universe. Throughout this journey, we have explored how the violation of symmetry in the fundamental laws of physics has shaped our cosmos. The expansion of the universe also presents us with an intriguing puzzle. As the universe expands, new structures and dynamics are generated. But what implications does this have for symmetry in the cosmos? It invites us to reflect on the impact of gravity and how this force can introduce asymmetries into the fabric of space-time. Another fascinating aspect is the relationship between entropy and time. Entropy, which tends to increase over time, also introduces a form of asymmetry. But what does this mean for our perception of time? It leads us to question whether time is linear or if there exists a form of symmetry that we have yet to fully understand. Throughout our journey, we have seen how symmetry and asymmetry affect not only physics but also life itself. Biological diversity, the structures of organisms, and even our emotions are deeply influenced by these concepts. Asymmetry has allowed us to evolve, adapt, and thrive in a constantly changing environment. Culture is also influenced by these ideas. Asymmetry has found its way into art, music, and philosophy, enriching our lives. It reminds us that beauty can arise from the unexpected, from the imbalances that surround us. Just as art challenges our expectations, the universe does the same by revealing its secrets. Looking to the future, it is exciting to think about the new research being conducted. The questions that remain unanswered keep us intrigued and motivated. What discoveries await us on the horizon? Science advances, and with it our understanding of symmetry and asymmetry in the universe deepens. As we close this cycle of exploration, it is essential to remember that the central question, why is the universe not symmetrical, invites us to continue inquiring. Curiosity is the driving force of science and life. It pushes us to seek answers, to question what we take for granted, and to marvel at the complexity of the cosmos. In summary, asymmetry is not a mere anomaly, but an essential component of reality. It teaches us that the universe is a place of contrasts and nuances, where every small imbalance can have a significant impact. At the end of the day, asymmetry contributes to the beauty and diversity that we all appreciate. So how does all this affect us in our daily lives? The answer is that by understanding the asymmetry of the universe, we can also better comprehend our own experiences. Each of us is unique with our own stories and challenges, and it is precisely this diversity that enriches our existence. Asymmetry is a constant reminder that amidst chaos and complexity, there is also order and beauty. And by learning to appreciate this duality, we can find a deeper meaning in our lives and in the vast universe that surrounds us. The exploration of symmetry and asymmetry is ultimately a journey towards self-knowledge and connection with the whole.